Hi everyone and welcome back to my channel. So today we'll start a new topic of computer organization and architecture. So today we'll learn instruction pipelining. Okay. So before starting today's lecture, I want to say this is a separate topic than all the previous topics, whatever we have learned. And please pay close attention to this because this is a very important topic for both GATE and placements. Because questions will get asked because this is a topic that has actually use case in the actual industry. So that's why this topic is very important, and many students do get confused with few like sections of this topics like hazards. So we will understand everything very clearly. This is important for both GATE and placements. Okay, so let's start. Like we can observe a picture here, right? What does this picture want to say? At the I hope at the end of this lecture you will be able to understand the difference between this and this. So I'll just give you a bit of overview. Basically what the first picture is doing, it is doing all the tasks, right? Here I have some I have 4 people with 4 laundry bags. All of them want to wash their clothes. So there can be 2 ways to go about this. One is, one person A goes here to the washing machine. He drops his laundry to the washing machine. Then there is another machine that is dryer. Then he takes out the clothes after the clothes have been washed and gives it inside the dryer, and then it dries. Then finally he takes out the clothes. Okay, and he finally goes to home. And after this whole transaction, I again call the person B. Okay, but there can be another way to do this as well. So while the first person is doing, we don't make any changes. Okay, first person does his first puts his clothes in the washing machine, then he puts his clothes in the dryer, then he went out. But as soon as the person takes out his clothes from the washing machine and puts in dryer, this washing machine, right, this is free actually. This washing machine is actually free. So what we can do, we can tell person B, come here. Okay, you can put your clothes in the washing machine because the washing machine is currently free. It is not getting used by anything, right? Dryer is getting used by person A, but washing machine is free. So you can utilize that time for which the person A is drying up his clothes in the washing machine. Then as soon as the clothes gets dried up, the person A takes out his clothes and the person B again puts his clothes in the dryer. Okay, then again the washing machine is free. Okay, so like this happens. We'll see more examples. I'm just giving you a overview. What happens? What is the difference between this? This is sequential. This is sequential processing because one process is totally independent of other. Person A washing the clothes is totally independent of person B washing the clothes. Okay, both things are totally independent. Okay, but here actually few things are dependent because when the person A is using the dryer, person B is using the washing machine. So few things are interrelated. We will understand those. So here what is happening is, this is a mode of sequential just hold on, sequential processing, and this is a mode of what? Parallel processing. So actually we have a few classification. This is a very old classification that Flynn gave. Now like basic things, they have just named these things. For the first classification of computers is single instruction, single data. What does it mean? A single processor executes a single stream of single instruction stream to operate on data stored in a single memory. So standard non-parallel computers use this. So the data comes in, like the instruction comes in, the processor processes the instruction, it does some operations on the operands, and then finally after this instruction I1 has been fetched, then only I will fetch the instruction I2. So how we go? First I fetch I1, then after fetching I1, after completing instruction I1, after executing instruction I1, I go to I2, then after executing instruction I2, completing instruction I2, I go to I3. So all of these, right, are happening in serial, okay, sequentially. Nothing is happening in parallel. So after only I finish my instruction I1, my first task, then only I will go to task 2. I will not go to task 2 simultaneously. How do we go simultaneously? I will show you with example. Today's lecture is about that only. Now next type of classification is single instruction multiple data. A single instruction operates on multiple data streams simultaneously. So what happens is, instruction is same, but I have to perform the same instruction in multiple data points. Let's say add AB. Okay, I have add AB here, or add like 2000 each, and 1000 each. And after every instruction, this address is getting incremented by 1. These are all addresses. Go to this memory location and add the operands. So then the next instruction will be 2001 each plus 1001. So I can actually do this. What I like, my processor is computing sequentially only, but it is processing multiple datas, multiple streams of data simultaneously. It will take all the data simultaneously, then add. Okay, it can do that. So this has like, this is what we do in pipeline. Okay, this is exactly not parallel processing. But this is like what I will show you example, like this example, right? Exactly, we are not doing parallel processing because we are not executing two instructions parallelly. No, we are not doing that. But what we are doing is we are allocating resources. So first I observe that washing machine is free. After person A has finished washing his clothes, he will put it in dryer. So washing machine is free. So I will allocate that resource until when the washing machine is free to person B. So here what happens? The resource allocation happens. So I'm doing some operations simultaneously, but what I can say is they are not exactly parallel. What do I mean by that? We'll understand that by the example, but just understand this is what we use in pipeline processing. Okay, pipeline processing, where we process the data simultaneously. Next is multiple instruction and single data. So like this is not possible sometimes to have, like we have multiple instructions and I'm operating on single data. This is mainly theoretical model because like if you have multiple instructions on the single data, your I1 instruction, let's say your I1 instruction is A plus B, right? So it will change the contents of A, B. It can. So there is just, it is a theoretical concept of multiple instructions, single data stream. Actually, we don't use this. Generally, it is used in fault tolerant systems where same data is processed using different algorithms. Okay, so the use case is this. Then is multiple instruction, multiple data. So this is actually what is known as parallel processing. So this is actually true parallel processing. This one is also a parallel processing, but not exactly, because I'm not exactly processing these two things parallelly. No, but a few things are common here, right? So this is in the gray area. Okay, so this is the true parallel processing where I have multiple processors for executing different instructions and they are happening parallelly. So this is true parallel processing. So like there are many types of parallel processing, so we'll understand those. So first one is array type, where employs an array of processors to execute tasks on multiple data simultaneously. So this is like MIMD. Okay, this is like MIMD that I have just told you at the end here, right? This is just that. Another type of parallel processing is there. Okay, so like what is that? That is like, what does parallel processing helps? Why does parallel processing help us? It helps because we can do simultaneously data processing of multiple instructions. So obviously our execution time of the whole program gets reduced, right? If your compiler, like if you have 100 lines of code and each line is an instruction, so it will take you, let's say each line takes 100 seconds. But if you have multiple processors which are like processor 1, let's say, is executing instruction I1, I2, I3, and processor 2 is executing instruction I3, I4, I5, or something like that. Okay, so obviously the execution time of the program gets reduced, so you save time. Okay, you save execution time, which is very, very important. Now what is parallel processing? What is the other type of parallel processing known as pipeline processing? So this is more like single instructions and multiple data. Okay, so this pipeline processing is actually not helpful everywhere. It is not helpful everywhere. We'll understand this. So this is like wherever I have a type of single instruction and multiple data, so I have to, like, similar instructions are there and I have to do it on multiple datas, then this pipeline processing will be helpful. We'll understand that slowly. It breaks down sequential process into sub operations performed across multiple stages. Like what is the example? Example is assembly line in factories, like producing cars on a assembly line. So in a like car, right, in an assembly line of a car, what happens first? Like I exactly don't know the process, but first you build up the structure, right? Or somewhere engine gets built, somewhere the suspension gets built, somewhere the tire gets built, and at the end finally you all what do you say, assemble that. So the engine getting built and the suspension getting built, are they sequential or they can be run parallelly? They can be run parallel, right? Because at some place I will have some production site for engine, and at some place I will have some production site for suspension. So those can happen parallelly. So we'll see those. And producing cars is what? It's a repetition of same thing, right? We're repeating the same thing only. If I am producing a car, we are exactly repeating it 1,000 times. A single instruction is producing, let's say, car XYZ, right? And we have to produce the same car only. Why will we produce a different car? Okay. So with the help of example, we'll understand this. Let's take a basic example. Pipelining is a method of decomposing a process into smaller subtasks, enabling simultaneous execution across different stages. Okay. So let's take an example. You are making a sandwich. So to make a sandwich, there are 3 steps. Okay. So this is my instruction. Sandwich making is my instruction. And I have broken down my instruction into small stages. These are actually known as, in technical term, known as pipeline stages. Okay, here they have also told different stages, right? Or subtask, you can also say subtask. So to make a sandwich, first you have to cut the bread. Okay, it takes you around 2 minutes. Then what you have to do, you have to apply butter and filling inside the sandwich, whatever filling you want. Like you want some chicken filling or some paneer filling or some like only vegetable filling. Okay, anything filling between those 2 sandwich, you fill that. So it takes, let's take an example, it takes you around 3 minutes. And to pack the sandwich, finally that has been done. You have to, like, it's like assembly, right? You pack the sandwich totally and give it to the end user, or you yourself want to take it to the like you or take it to office or class. After on lunch you will eat that. Okay, so these are the different stages. Now each of them takes 2 minutes, 3 minutes and 2 minutes. Okay, so if I am not using any pipelining, right, making each sandwich, so let's say you want to make 10 sandwich, making each sandwich will take you how many minutes? Pause the video, answer in the comments below how many minutes. If we are not using, like for those people who know pipelining a bit, they can answer. Who don't know, don't worry, I will tell you the answer. Okay, I will explain. So without pipelining, how much time will it take to make each sandwich, and with pipelining, how much time it will take for a new sandwich to get ready after the first one? How much time the next sandwiches will take for me to get ready after the first one if I am using pipeline? So without pipelining, it is just sequential processing. So first I will cut the bread, then I will apply the butter and filling, then I will pack the sandwich. So first sandwich is done. Then only after the first sandwich is done, then I will come back to the second sandwich. So each sandwich is taking how much? 2 plus 2, 4 plus 3, 7 minutes. 7 minutes. Now, someone smarter, okay, like a big company CEO or something, came to your place and told you, yeah, Rakesh, actually we can do it a bit better. What we can do is, we have this 3 tasks, right? 3 stages we have. So we can assign individual person to each of these stages. So there is person A to cut the bread, there is person B to apply the butter, and there is person C to pack the sandwich. So there is person A, B and C. Now they are different person, so they can do tasks simultaneously. So that is what we will do. So here what we do is, in timeline between 0 to 1, the first sandwich, person A will do what? Person A will cut the bread, and person B and C will simply sit idle because they don't have anything to do, because bread hasn't been cut yet. So as soon as person A cuts the bread, he sends it to person B. So person B gets the cut bread, right? Now what is the task of person B? The task of person B is to apply butter. So person B applies butter. Okay. Just I will technicalities I will come to later on. For now, just understand the basic things. Okay. Okay, one thing. This has been a bit wrong actually. I will just edit this small thing. this is wrong. This is wrong actually. I will update this. Don't worry about time right now. I will update this. Okay. So, what I can say is this is taking 3 minutes. Okay, fine. Or what we can do, right? We can actually change a small data point. Okay, no, we don't want to change the small data point actually. That is enough. I told you, right? Person A has cut the bread and he has sent to person B. Okay, so person B currently, so this is from minute 0 to 2. Minute 0 to 2, and person B from minute 2 to some other minute. Person B is doing what? Person B is applying filling to the sandwich 1, but simultaneously person A right now is like he is free, right? Person A is free, so I can give him the sandwich 2 and tell him, but you are free right now, so cut the bread right now. You can cut the bread, right? For cutting the bread you don't need anything else, so I will give him the sandwich 2 and he can cut the bread. But in the same, like from the same time, person B is also doing the work, but person C is ideal right now. Okay, person C is ideal. Now I come back to third stage. Okay, I will not tell you the time right now. Time is a bit I will tell you the time. Time is a bit confusing. But at the third situation, third step, so person A has finished his cutting his sandwich 2. He will send it to again person B, because person B also has finished his filling. Person B will send it to person C for final like packing the sandwich, right? So now all the 3 persons are doing the work simultaneously, right? But they are doing different works. So here there is simultaneous execution across different stages. They are not doing the same task. They are not adding, like let's say there is an add instruction, right? So they cannot add simultaneously, but they are doing like separate task. Okay, different stages. So this is like this is cutting, like person C right now is packing the sandwich. Person B right now is filling the sandwich for the second sandwich 2, and person A is cutting the sandwich for the third sandwich. So parallel operation is happening. Now you might say, why is this so much useful? Why is this so much useful? The useful comes here, right? Comes here at the output. So for the first stage, it doesn't make any difference. Okay, it will take the same time. For the first stage, it will take the same time. But for the second stage, for the first sandwich, it will be same only. For making the first sandwich using pipeline instruction or non-pipeline instruction, it will take the same time. But for making the second sandwich, right, it will not take us much time. It will not take us much time. So why? Why is that after this, right, after this packing portion is happening, at every cycle, like after every jump, I'm getting a new sandwich ready. Because all 3 are actually working parallelly. Okay, all 3 are working parallelly here, but they are doing different tasks. So as soon as I come here, right, so as soon as this person C will send this sandwich to the output, to the tiffin box, person C will again receive sandwich 2 instantaneously, and person B will receive sandwich 4, and person A will receive sandwich 5, like that. It will go on. After every cycle or every jump, I am getting a sandwich ready. Now what is the duration of this jump? That we'll understand. So a basic idea, I hope you understood. We have more examples, don't worry, we'll understand this more. Okay, so one thing is there, I want to do task parallelly, but I want to do different tasks. So how much gap should I give to each person? So person A and person B and person C, I would give them some time, right? Because if, for example, you tell person A you take 2 minutes, person B you take 3 minutes, and person C you take 2 minutes, what will be the problem with this? If they don't have a common time, right? If all the 3 stages don't have a common time, what will be the problem? So first here person A does from 0 to 2, does cut the sandwich, and he finishes the sandwich. So from 2 to what? This is the important. To do what? He will, like from 2, he will send to person B, who will apply the filling. So from 2 to apply filling, how much time do I need? I need 3 minutes. So it will be 2 to 5. Okay. But there is a problem. In 2 minutes, right? This person A will say, man, I have finished cutting my sandwich. What I will do? You have told me to not sit idle. So I will send this sandwich to the person B. But this person B will tell me, I am still working on something, right? I am still filling the bread. You have given me 3 minutes to fill the bread, but only 2 minutes have passed, right? After, like, this cutting of sandwich 2 will be finished by when? It will be finished by 4 minutes. Still I have 1 minute left for this person B to finish filling. Okay. But person A will say, instruction came from the CEO. He has told to apply like this, that whenever I finish my job, I will send it to the next stage. But person B will tell, I don't have free space right now. I have to first fill the sandwich, do this task, then I can fill the next sandwich, right? So there is a problem here. So to nullify this problem, to get around this problem, what we do, we have a common time. And this is also known as synchronous pipelining. This particular thing known as synchronous pipelining. What we do is, we take the maximum of all these stages. If I take the maximum, right, there cannot be any overlap, because it can't happen that I have taken the maximum time and person B, person A will finish cutting the bread in more than that. Person A will finish cutting the bread in only in 2 minutes. It will not take 4 minutes, right? If I choose the maximum out of these 3, my duration cannot go above that. So I will choose the maximum so that I have enough headroom for no overlap and no confusion. So what I do, I will choose a maximum. So this maximum of T1, T2 and T3. Okay. This step is actually known as also synchronous pipelining, because everything is in sync. Synchronous pipelining. All the time is same. It is not different across the each stage. That's why it is called synchronous pipelining. So a new sandwich is ready after the first how many minutes? This problem we haven't yet solved, but what we have solved is, we have found out the duration of each stage. So we'll choose the maximum. Maximum here is 3 minutes, right? Out of all these stages. So I'll choose 3 minutes. Okay. So that's why I actually deleted this previously. So this will be, each stage will be 3 minutes. They are also sometimes known as cycles. So from 0 to 3, I will give the person A to cut the bread. And you will say, sir, person A will sit idle for 1 minute. It's okay. It's fine. That is fine. Okay. Why that is fine, we will understand that later as well. But it's okay. Let person A sit idle for 1 minute. That is fine. But I cannot give it after like 2 minutes only. That is the issue, right? There will be some overlap. Person B will crib about that thing. Okay. So from 3, again, each cycle will be of 3 minutes. So this will be from 6 to 9. Nine to 12. This will be from 12 to 15. So what is happening here is, from 3 to 6, after 3, sandwich 1 goes to person B, and at 3, sandwich 2 comes to person A. So now person B will take 3 minutes totally to filling, and then it will send to person C. So there is no overlap. And as soon as it sends to person C, person A, after 3 minutes, that is at 6 minutes, it will send to person C the sandwich 2, and person A will receive sandwich 3. So after this, right? After this, what is happening is, after every cycle, after every 3 minutes, a new sandwich is getting ready. If I observe here, person C is receiving the sandwich 1 at 6 minutes. Then it will again take 3 minutes. I will give it 3 minutes to complete its task, and it will hand it over to the lunch box. Then again at 9, person C will receive the sandwich 2. Again it will hand it over to the lunchbox after 12, after 3 minutes. Again at 12 it will receive the sandwich 3. Again it will hand it over to the lunchbox. So at every 3 minutes or at every cycle, my sandwich is getting ready. So each instruction gets gets execute, to be technically correct, gets execute in just every clock cycle. So isn't it so fast? Because how much time it is taking me for each sandwich to get ready? 3 minutes. 3 minutes. Okay, this is 3 minutes. Isn't this huge? This will be even huge when the tasks are very larger. Okay, and I can use pipeline on those. But there is a just caveat that you need to understand is we can only use pipeline processing for similar types of tasks. If you are repeating it 100 times, then only pipelining is useful. Just like I'm making sandwich and it is a repetitive task, right? So if I'm making sandwich, it is a repetitive task, we can use pipelining there. Okay, because making 100 sandwich will take me very, very low amount of time, because after every clock cycle a new sandwich gets made up. Okay, so that is where this pipelining comes into the picture, useful for repetitive operations on multiple data inputs, only useful for repetitive. This is the most important point. I know you will forget this point. Okay, pipelining is useful only for repetitive operations, not for everything. Okay, so here this is a bit wrong. Total time for each sandwich, right? So how much total time did it took me to make 3 sandwiches using without pipelining? Each sandwich will take 7 minutes, so total 3 sandwich will take total 21 minutes, right? Because it is without pipelining, everything is working individually, okay, independently. With pipeline, you will observe that the first sandwich gets ready at 9th minute. Okay, first sandwich gets ready at 9th minute. After that, right, my sandwich 2 only takes 3 minutes more, and my sandwich 3 also only takes 3 minutes more. So this is a bit wrong. Only the first sandwich will take me more time to make, that is 9 minutes, and after that every sandwich will only take me just one clock cycle, that is 3 minutes. So it will be totally 15 minutes. Okay, so obviously I'm saving 6 minutes, and which is huge. It is like almost 30% savings. Okay, so I hope you have understood the thing that I wanted to explain using this operation. Okay, so here, right, I just want to write down neatly so that you can understand, if you ever come back to device. At this stage, this is ideal. Person B is ideal and person C is ideal. But in this period, right, in this time period from 3 to 6, only person C is ideal because instruction 1 hasn't been executed by the person B. And after this, right, from this stage onwards, okay, from 6 to 9, you can observe all the 3 persons are doing some work. So it is known as parallel operations of different stages. They are different stages. Parallel operation of different stages. Okay. So let's now understand what happens actually in our programs. So we use, like, this concept is known as pipelining. Like this concept, right? This concept of parallel processing, each processing happening in different tasks, is known as pipelining. Okay. So this is a concept. Okay. Why do we call it pipelining? Because if you observe, it is just like a pipe. Why it is like a pipe? If I place a pipe here, right, and for the first time this pipe is empty, then I put sandwich 1 here. Okay, so the sandwich 1 comes in this is, let's say, this is the stage 1 of the pipe, this is the stage 2 of the pipe, and this is the stage 3. So S1, S2, S3. So it takes the bread comes here, stage 1, then it goes to stage 2, then it goes to stage 3. So my first bread is here, then the second bread comes after that, it goes to stage 2, and the third bread comes here, it goes to stage 1. So it takes some time for the pipe to get filled. After that, what happens? If the pipe is filled, right, if the pipe is filled, okay, this is my bread, uh, bread 1, bread 2 and bread 3. 3 breads are filled. So after that, if I put in one bread, right, this is bread 4, the first bread will come out here, correct? Then again, if I put the fifth bread, the other bread will come out here, bread 2 will come out. So it's just like pipe. As water enters, it takes some time for the water to get overall filled in the pipe. Then the water just flows, right? Water comes in and goes out, comes in and goes out. There is no delay. There is no delay actually. So that is the concept that we're using. That's why it is called pipelining, because it just flows like through a pipe, right? Each instruction flows through a pipe. Okay. So we in COA, we use this concept known as pipelining. Pipelining is a technique used to break sequential processes. They have to be sequential, do remember, into smaller sub operations which are executed in different stages, also called as segments. Each stage works on a separate part of the process. Each stage works on a separate part of the process, allowing multiple inputs to be processed simultaneously. So here, right, from minute 6 to 9, multiple inputs are getting processed, right? Sandwich 1, what is happening to sandwich 1? Packing is happening for sandwich 1. What is happening for sandwich 2? Butter and filling is happening for sandwich 2. What is happening for sandwich 3? Cutting of the bread is happening for sandwich 3. So parallelly, a lot of things are happening between this 6 to 9 period, right? So that's why it is telling here that we are doing process simultaneously. Okay. So here task is divided into multiple sub operations. All segments operate parallel except during the first time. Okay. The first time this sandwich 1, the pipe has to be filled, right? Except for the first time, each stage operates parallelly. Okay. So except initially when the, just hold on, except initially, okay, I think my spelling is also wrong. When the pipe gets filled, so it takes some time to get filled, right? Except that every stage it processes simultaneously. Okay. So increases efficiency by overlapping tasks. So here, like, tasks are overlapping because from this minute 6 to 9, period 6 to 9, multiple tasks is happening. This is doing packing, this is doing butter filling, this is doing cutting. So multiple tasks are happening simultaneously. That's why we do overlap, but not of same task, because this person A can only cut one bread at a time. It cannot cut 2 breads at a time. So it has only 2 hands. So I only give it the task of cutting, but 1 bread at a time. So that's why it increases efficiency by overlapping tasks, the different task. Okay, the different task. This improves the system throughput. What is system throughput? The definition of system throughput, we will understand this in today's lecture. Don't worry about this. So what is happening here? Generally, what we do is, like in instruction pipelining, I have multiple stages. So let's say I have 4 stages. So each instruction I1 will come here. Then there will be one buffer register that stores the instruction, right? Or the operand. Then instruction phase happens and it processes that stage. Like that stage has been processed. Then it doesn't, we directly don't feed it to the next stage. What we do, we keep it at a buffer register. Why? Due to this, right? Due to this differentiating, due to this maximum. Because person A has finished. He has finished his task. He will say, I have finished my task. I want to send. But person B won't allow to receive, right? Because he hasn't finished his sandwich 1 yet filling. So what we do is, we have a placeholder. We have a register. When as soon as person A finishes, he finishes his task in 2 minutes only. But we place it in buffer register. Okay, we place that finished task in buffer register at a plate. Let's say at a plate, right? There is person A. I will show you the example. Where can I show the example? Here, okay. I can use a new page. Okay, so I have here person A. Okay, he's cutting the bread. Then I have a plate in between, right? So person A finishes his task in 2 minutes, and then he keeps the bread in a plate. Okay, and it remains in the plate for 1 minute. Then again, what happens? I have person B. He can only take after 3 minutes, right? So he will take this bread after, like, the bread has been here for 1 minute, then only it will take the bread. And again it will do some operation, like it will fill butter and all those things. And after that, there is a plate. Okay, but this time the bread won't stay here for much long, because that is the maximum time that I have given for each instruction, right? So what will happen is, instantaneously this bread will come here and it will not stay here, and it will go to the next stage. And again it will take 2 minutes, and then again there will be a plate. Again there will be a plate here. Okay, so like this plate is just the buffer register. I just wanted to show you an example what is actually happening. The buffer register, it stores whatever computation has been done into a register, and then we pass it on to the next stage. Okay, so that everything can happen smoothly. Everything is in sync, everything is in synchronizing properly. Okay, so the same thing is written here only. Okay, okay, same thing is written. This is not something different. Okay, so anyways, this is not of much use. We can delete this page. So let's take a actual computer example, and with this we'll understand this like example more better. So we have a task, compute di. It is an array. Okay, let's, like, d is an array, x is an array, y is an array, z is an array. So it is only useful for similar type of instruction. So we are doing similar type of instruction for I equals to from 1 to 6. I am doing same type of instruction. What I am doing, I am taking the first element of x array and adding it with the first element of y array, then multiplying this whole thing result with the first element of z array, and then I am storing it in some d array of the first element, and I am repeating this process. I am just doing the same thing only for different datas. Datas are different, but instruction is same. So pipelining is useful only for similar types of instructions. So pipelining, although I have mentioned this, like I have repeated this many times, but still I wanted to clear this thing. Pipelining is useful for similar type of instruction. Okay, so can I break this down into sub operations? I've already in my mouth as well, I have told you, like, how can we break it down into sub operations. First, what we do, we load the data into registers R1 and R2, this xi and yi. Then we can perform the addition operation and store the result in some register R3. Then I can load this data zi into register R4. Then finally I can do the multiplication operation of the contents present on R3 and R4. Then finally I can store the result in R5. So these are each sub operations. So there are total 4 stages. Okay, there are total 4 stages. Here I think you have seen something, that instruction fetch, instruction decode, instruction execute. So this is just like how a instruction cycle is, right? So we break down our instruction cycle into 4 stages, and we use instruction pipelining. Okay, that I will come to later on. For now, just understand this basic thing, right? That we have broken down this whole instruction into smaller stages. Okay, so how can I write the micro operations? What are the micro operations? So for the stage 1, the micro operations are what? Micro operations are I am storing the value of xi in R1 and storing the value of yi in R2, and then I am adding R1 and R2. That is another micro operation, and storing it back in R4. So R4 is getting stored by R1 plus R2, not R4, sorry, R3. Then I am loading the zi value on R4. So R4 the value is getting loaded. Okay, Zi value is getting loaded. Then what I'm doing, I'm multiplying R3 and R4 and storing the result in R5. So R5 is getting stored by the result R3 into R4. Okay, so these are the micro operations that are happening in each stage. So like that is what is written. Stage 1 we load this thing, stage 2 we perform addition, stage 3 perform multiplication. Okay, and like this, right? Okay, this loading, like I have, like what we can do, we can club the things, we can also club few things if it is possible, because these two tasks, right, seemingly it depends on the architecture, but here I have taken a assumption that I can perform these two in a same stage, in a single stage, adding the contents of R1 R2 and storing it in R3 and storing the contents of Zi in R4. I can do this simultaneously, so we don't need 4 stages. So that like this also we can reduce the number of stages. So what is happening in hardware level? So this is just a pipe, right? So this is the hardware diagram actually. So what we do is, first my xi and yi will come from will get loaded into R1 R2. Then I will have an adder, and then this result of the adder will be stored in R3. And then finally what I'll do, I will like this R4 and this R3, right? This is happening simultaneously in stage 2, storage of value of Zi in R4 and this getting the result in R3. This is happening in stage 2, and then finally I am passing it by a multiplier at the final stage, which is then the result of this is stored in R5. Then obviously that is my DI. So I hope you have understood the hardware level diagram. What is happening hardware? So this is just like a pipe, right? Just like a pipe. Okay, just like a pipe. This is just like a pipe. Why this is just like a pipe? Because data is flowing in here and it is coming out of this, right? And after the first iteration, each time it will just take me whatever each stage takes the time. Okay, for like fetching a new instruction, it will not take me much time, because for the first time only water needs to come in and fill the pipe. After the pipe gets filled, it will not take me much time for the water to get out as the water comes in from on the other side. Okay, in and out. So this is the hardware level diagram. So let's together solve. Okay, let's together solve in each stage what is happening. So what happens is, we actually perform operations according to clock cycles. So each clock cycle will perform a task in each stage. Okay, so in the first clock cycle, in stage 1 what will happen? In stage 1 I will load my x1 and y1. All the other stages will be idle, person A, B, C. Okay, so I will load here. Load my x1 and y1. Stage 2 will be simply idle. Nothing will happen, right? Because stage 1 hasn't even processed the data, so we cannot do anything in stage 2. And stage 3 will also be sitting idle. Okay, so this is just the first iteration, right? Then in second clock cycle what will happen? Second clock cycle, stage 1 has performed its task. It has loaded the value in x1 or y1. It will pass this same thing into stage 2, like this here, right? Stage 1 has performed its task. It will pass it to the stage 2. Okay, so stage 2, what is the task of stage 2? The task of stage 2 is adding x1 plus y1. Okay, addition. Then also the task and loading it in R3. Actually, this is log, right? Yeah, this is log. So adding x1 plus y1 and loading this value in R3. Also loading the value of z, that is z1, in register R4. So this is the task of stage 2 in cycle, clock cycle. This is t equals to clock cycle 1 second, 2 second. Each cycle takes 1 second, you can assume. Okay, in second clock cycle also, I will not keep stage 1 idle. Okay, stage 1 has done its job in first clock cycle. It has sent the data to the next stage. So I can simultaneously send x2 and y2 in stage 1 in the second clock cycle, because it is just sitting idle there. It has already performed loading and just send it to the next stage. So in second clock cycle, this is just sitting idle. So what I will do, I will just load load x2 and y2. Okay, I'll just simply load x2 and y2. Okay, but again stage 3 will still be idle because again the previous stage hasn't processed its data, so for it to receive, right? Stage 3 will be idle here. In the third clock cycle, what will happen? Stage 3 will receive the data from the stage 2 because it has performed the operation, it has done its job. So what was the task for stage 3? The task for stage 3 was simply perform the multiplication operation and store it in register R5. So what it will do? It will do R4 R3 into R4 and store this thing in R5. Okay, so simultaneously in the third clock cycle, what will stage 2 do? It has performed its operation in the previous cycle, right? It has already performed its operation in the previous cycle. So what it will do? It will take the values of x2 and y2 and perform the same operation. It can do it because it has performed this operation in the previous cycle. So of x1 y1. So what, again the same thing will happen here, that my R3 will get loaded, okay, with x2 plus y2 and R4 will get loaded by z2. There is a problem here that will come to later on. For now, just assume there is no problem. Okay, so why am I telling you a problem? We will understand in the hazard chapter. So this is happening, right? So in stage 1, what will happen? Again, I will load my registers R1 and R2 with this, right? So what I actually, these were the micro operations. R1 was supposed to get loaded with x1 and R2 was supposed to get loaded with y1. And here my R1 is supposed to get loaded with x2 and R2 is supposed to get loaded with y2. And here my R1 is supposed to get loaded with x3 and R2 is supposed to get loaded with y3. Okay, so that is the case over here. So now simultaneously what can happen here in this clock cycle, fourth clock cycle, what can happen? Simultaneously it can actually get the perform. Okay, it is okay, something is this x2 y2. Sorry, I'm wrong. That's where I was wrong, right? Actually this will be here. This, right? This will be just y4 x4. Now at each clock cycle a new instruction gets fetched. Okay, this will be 4, this will be 5, this will be 6. Okay, now here also same thing is happening. I am applying operation on the previous instruction, right? So previously this has already fetched x3 and y3, so I can do operations on x3 and y3 actually. x3 and y3. Okay, so it will do x3 y3 z3 and this also is the same. Again this will come where? Here, right? This will come, this operation will happen here. So this will do R5. This is the same only. This is doing the same only. Okay, nothing different. So this is R3 getting stored here of x4 and y4. This will be 5. Okay, so like this will go on like this. I will not complete all the examples. Okay, this will go on. So what is happening? Basically first I fetched the data here, then it came to the next stage in the next clock cycle. Then again, after operation on this next stage, then again I went to the next clock cycle, and then finally I got my output. Same thing is happening here as well. Same thing is happening here as well. At each clock cycle, my data is flowing through the next stage, right? So it's just like a pipe. Data is coming in this pipe, okay, and then the data is coming out of the pipe, okay. So that is what is happening. So this is how a pipeline works basically. I hope you understood with a basic example. And here I have 6 iterations. So homework is you can complete this table for 6 iterations, and as soon as I get here 6 iterations, right, the first few stages will be idle because they don't have any new data to fetch from, because I have only 6 data, right? So now let's do a basic comparison. If I would have used a non-pipeline processor, right? Non-pipeline processing, that is sequential processing. Sequential processing. Okay, sequential processing. So if I use sequential processing, what does that mean? That means that each of the instruction will individually take its own time. Each are independent. So first of all, I will not do like this, that okay, this is currently fetched, stage 2 has this operand, so I will fetch the x2 and y2 in stage 1. No, I cannot do. First of all, these whole thing has to be finished, then only I can fetch this x2 and y2. So each are independent. So how many clock cycles each stage is taking? 1 clock cycle. My assumption is 1 clock cycle. So what will be the total time? Total time T, okay, for non-pipeline. It will be equal to what? It will be simply time taken to perform each instructions multiplied by the number of instructions. Okay, so everything is individual. First instruction will take 3 cycles. Next instruction will take another 3 cycles, to total 6 cycles. Next instruction will take another 3 cycles, 9 cycles. So each instruction is taking how much? 3 cycles. And total how many instructions I have to do? How many data elements I have in the array? 6 elements, right? Total it is going from 1. It is going from 1 to 6. So how many elements I have? 6. How do I calculate the number of elements? Just remember this basic thing. To calculate the number of elements between 2 numbers, what you do? You write the final number minus the initial number plus 1. Okay. This is, remember this thing. This will be very, very helpful in future. Trust me. This will be very, very helpful. This is final. This is initial. And this plus 1 will be constant. This plus 1 will always be there. This calculates the number of elements between 2 numbers. So this actually becomes how many? 6. Total 6 instruction, number of instructions I have. So it will be total 8 cycles. Now for the same case, if I now have a pipeline processor, okay, this one, let me add a new page. That is a huge problem actually. Just hold on. There's a huge bug here. Okay, yeah. If I apply my concept of pipeline processing, then how much time it will take me? This will be pipeline processing. If I apply pipeline processing, right? So total how many cycles I will require? So for the first time, I am requiring 3 cycles. First time I am requiring 3 cycles. But afterwards, after how many cycles I am getting a new result? After 1 cycle only. So for the first time, I required 3 cycles. Then as soon as I get my first result, right, after that I only take one cycle to get the next result. Okay, I only take one cycle. So what is the significance of this 3 cycle? What is this 3 cycles actually? This 3 cycle is actually the number of stages. This 3 cycles is the number of stages. Okay. So, and as soon as I get my first instruction, how many instructions left? 5 instructions are left. Total there are 6 elements, right? Only 5 elements are left. So how many total number of cycles it will take me? Total number of cycles will be equals to, for a pipeline processing, will be equals to number of stages. So this time is taken for what? This time is taken to execute the first instruction. Okay, to complete the first instruction. To execute the first instructions. After this, I will just take one cycle for each instructions. So how many instructions are left? One instruction has already been executed. How many are left? Let's say I have n instructions. If I have n instructions, right? So like if I have n instructions, a non-pipeline system will take how much? It will be t n into tn. This is my non-pipeline. What is this tn? Tn is the time. Tn is what? Tn is the time taken to perform each instruction. Written over here, right? Tn is the time taken to perform each instruction, and I have n number of instructions, so it will be ntn. And here, how much time it will take? Here, actually, like although I have written here cycles, I can write this in terms of time as well. Okay, this is written in cycles, but time cycle, it's the same thing only. Okay. So here, what is actually happening? Like what you can do is you can also skip the number of time taken to perform each instruction. Yeah. So total each okay, because I have 18 cycles, right? Yeah. Here what you can do, number of stages is fine, plus the after each cycle I'm getting a new instruction. So I will require how many cycles? Total I have n instructions. One has already been executed. How many are left? N minus 1. So it will require me n minus 1 cycles. So remember, this is the number of cycles. Okay, cycles. Let's assume that each cycle takes some TP time. Each cycle time is TP time. Some common time has been given. Okay, I have given some common time TP. So total time for pipeline. Okay, pipeline processing of the same task. It will be what? It will be, we write this number of stages. This has a notation that is k. We denote it in terms of k. K plus n minus 1 into TP. TP is the time taken for each cycle operation. So here how many cycles we are actually requiring? Here if you observe, I have 3 stages, and after that how many instructions are left? Only 5 instructions are left. Total pipeline cycles, how many pipeline cycles I will need? 8 cycles. So in our example, I had 3 stages plus 1 instruction has been executed. So I have 5 instructions left to be executed. So it will be 5. This will be equals to 8 cycles. But here in parallel, in sequential processing or non-pipeline processing, it is taking me 18 cycles. So I'm saving 10 cycles. What if I tell you, you increase the number of instructions of similar instructions? What if this n increases? If this n increases, let's take an example. Okay, let's take an example. If n is 10 now, so I have 10 array size, right? Array size is 10. I'm performing the same task on 10 data points. Okay, so now how many cycles will take me? So this is non-pipeline and this is pipeline. How many cycles it is taking me? If n is 10, right, it will take me 10 times whatever the time of each cycle is. Okay, because like what are the number of stages are? So each instruction has 3 stages, so it will be total 30 cycles. It will be total 30 cycles. Okay, 30. But for pipeline, how many number of cycles it will take me? For pipeline, I have the first instruction will take total of 3 cycles. Fine. But then how many cycles it will take? Just 1 cycle for each instruction. How many instructions are left? N minus 1. Total I have 10 instructions. 1 has been executed. 9 I have left. That is n minus 1. That is 10 minus 1 is 9. So it will be 3 plus 9. That is 12. If I increase n to 100, how many cycles it will take me for the non-pipelined architecture? It will be 100 times the number of stages for each instruction, that is 3. Total cycles it will be 300 cycles. For pipeline, how many? For the first instruction, again it will take me only 3 cycles. For every other instruction, it will only take me 1 extra cycle. How many instructions are left? 1 instruction has already been executed out of 100. 99 and 9 are left, that is 100 minus 99, that is 99. 100 minus 1, that is 99. So it will be 102. Can you observe the difference here? This is almost 1/3, right? This is almost 1/3. This also is 1/3, but little greater than 1/3. This is almost 1/3. So I can observe the number of cycles, right, is very, very lower compared to non-pipeline architecture. So what is the difference like between non-pipeline system and pipeline system? So basically we get increased efficiency. As task increases, the pipeline processing becomes significantly faster than non-pipeline processing, as can be observed with the basic comparison, right? And performance difference. In non-pipeline processing, each task is completed sequentially, while pipelining overlaps operations, reducing the idle time and maximizing throughput. Basically it utilizes all segments, right? In sequential, what was happening? When I was going sequentially, right, first I was utilizing stage 1, stage 2 and stage 3 was idle for sequential or non-pipelined system. Then as I reached stage 2, in the second cycle, stage 1 and stage 3 are idle. But in pipeline, what do? We make stage 1 work. But in sequential, the stage 1 is idle because we are utilizing each instruction independently. Okay, so here what we can do, then at stage 3, what is happening? If I am using non-pipeline system, then my stage 1 and stage 2 will just sit idle in the third clock cycle. Then again this will repeat. So at each clock cycle, 2 segments are idle. So that is so much waste of resources, because these stages can work on the next instructions, right? Which have similar data, which we use in the pipeline system. So that's why pipeline is better than non-pipeline, but for only similar types of instructions. Because like this instruction is same, right? I'm doing this same operation on a array of data. So this operation doesn't change. If this operation changes, then the advantages of pipeline processing will also change, because this has changed, right? So it will be not sequential anymore. Data in, data out won't be same. Just like you have a pipe for water. Okay, this is a pipe. I will just show here only. You have a pipe for water. Now you won't be using the same pipe to carry oil. Okay, pipe for oil will be separate. Okay, it will have some different thickness, all those things. And sewage, you have another pipe for sewage, right? Sewage and waste, whatever it gets, sewage. So that also will have a different type of pipes. So different types of pipes will be different, but for the same item, right? It will go through water, it will go through oil, this will go through sewage. That will reduce with pipelining, but if the instruction itself is different, right, then obviously that our advantages, whatever we have gained with pipeline processing, won't be there anymore. Okay, but still it will be same as sequential only. Okay, but still it will be better. Like if I have like a pipeline system will always be better than a non-pipeline system. Okay, so that is what is written in the here, right? Pipelining versus non-pipelining. So if I see a graph, right, as I keep on increasing my number of instructions, what do I see? This is the time taken for a non-pipeline processor, okay, or the number of cycles. I see that gap, right? This gap keeps on increasing as the number of instructions get increased, right? Because in case of pipeline, the number of instruction gets increased and it is linear. So does the processing time. But in case of sequential, the number of instructions are getting increased and each instruction has 3 cycles. So it is getting increased by thrice. The number of cycles is getting increased by thrice. Here number of cycles only is incremented by 1. Okay, so that is the difference. That is the power of a pipeline processing that has been represented here by the graph, comparison of the graph. Okay, so there is a term known as pipeline cycle time. Now we are going into the technical terms of a pipeline processing. Okay, so what is pipeline cycle time? Pipeline cycle time refers to the time required for one stage of the pipeline to complete its operation and pass its result to the next stage. Okay, this cycle time is determined, this is also known as cycle time, is determined by the slowest stage in the pipeline since all stages operate in synchronization. As explained at the starting of the lecture already, that if I have 4 stages, 4 segments, and each of these segments has different time, like obviously, right, for fetching the instruction, it will take lesser amount of time. Let's say 5 nanoseconds. It is just fetching the instruction from the memory. Decoding, it is going into the control unit, right? It may take more time. So it is taking it 8 nanoseconds. Execute, it depends, right? It depends on the type of instructions. In our case, our assumption is execute is taking 6 nanoseconds. And write, then after I execute, the ALU has done some arithmetic operations. It needs to write back to the memory, right? So it takes 4 nanoseconds. So these are just assumptions. Now, can you tell me what will be the pipeline cycle time here? Obviously, many students may think I will choose 4 nanoseconds. It is best because it is taking the least amount of time. But if I choose 4 nanoseconds, right, all these stages, stage 1 to 3, all this will not be able to complete their task within this 4 nanoseconds. So obviously I will have to choose a slower so that all the other stages can complete its own task. It's okay that yes, if I choose my pipeline time TP, okay, TP to be 8 nanoseconds. If I choose my TP to be 8 nanoseconds, then obviously what I can say is that this stage 1, right, it will have 3 nanoseconds of idle time. 3 nanoseconds of idle time. Because it will obviously be done with its own task by 5 nanoseconds. It's okay. That's fine. But obviously I cannot choose 4 nanoseconds because it won't be able to finish its own task within 4 nanoseconds. It needs 1 more nanoseconds, right? So obviously it's better to sit idle than to not finish the task itself, right? So that is what our aim is. So we write this as TP clock, we write. Okay. So what we do is like this, right? This is what, if you know, this is basically a instruction cycle, right? Instruction cycle. So what we'll do, we'll utilize each instruction and we'll process them using pipeline. So although this execute, right, this execute is different, but each instruction has this 4 types of stages, mostly 4. It may depend. Okay, we'll see more examples, we'll understand that. But mostly they have 4 to 5 things only. First, it fetches the instruction, then it decodes the instruction, then it executes the instruction, then it writes back. Okay, if there is a memory read, memory write, all those things are there. If I need to fetch the operands as well, that will take some extra stage. That is for a separate discussion. But mota, basically, they contain this number of stages. Okay, so they're containing 4 stages, and I can use my concept of pipelining in this instruction cycle. Okay, so that is what we do. We use the concept of pipelining in instruction cycle because all instructions will have similar type of stages only, mostly. Okay, just the execution will change and the decode, internally things will change on depending on the operands and the instruction, but these 4 stages will be similar only. Okay, so what will be pipeline execution time? Already we have computed it, right? So if I have n task and I have k segments, right? So For the first, how many cycles it will take? How many cycles it will take for the first instruction to totally execute? It will take it k cycles. Then how many cycles will it take to execute the next remaining instructions? Total I have n tasks. Already I have finished my one of the n task. So how many tasks are left? I have n minus 1 task. So it will be plus n minus 1. So this is the number of cycles that the pipeline processor will take. But what is the pipeline execution time? I know this is the number of cycles. I know how much time does each cycle consume. So if I just simply multiply this by TP, I will get my pipeline execution time. So this will be multiplied by TP. So this will give me the pipeline execution time. So TP execution. TPX. Okay. TPX is the pipeline execution time. Now, obviously you can remember this, but if you understand this conceptually, you don't need to remember. First, if you this tells everything about pipeline processing. This first letter tells me that how many number of stages I have. So I finished the number of stages. So one instruction has been done. Next, remaining n minus 1 instruction will take how many cycles? Same number of cycles. Number of instructions will be equal to number of cycles, that is n minus 1 cycles, because at every cycle I am getting a new I'm getting the result of a new instruction. So this is the total number of cycles that I have already derived as well. And this is the time taken by each cycle, pipeline cycle time, and this will give me total execution time. Very simple, right? And in a non-pipeline processors, every task is executed sequentially. So here, this I know many students get confused that this TP and they confuse with this TN. This TN and this TP are different. Sometimes they can be same, but mostly you will assume it to be different. Okay, what is TP? TP is the pipeline cycle time. That is time taken for the pipeline to complete each segment. Okay, each segment. And what is TN? TN is the time taken to perform single task for a non-pipeline system. Now, how do I understand the difference? With example. Okay, with example I will understand. But first, let us derive the formula. So here, right, this will be T execute, TP execute. Okay, and this will be TNP non-pipeline execution time. What will be this? This, right, this I can, just the notation can be more better. So non-pipeline, right? Each instructions to perform each task, I require Tn amount of time. If I have n number of tasks, so how many tasks I have? N tasks. So how much time will it take me? It will take me n times Tn. Okay. Now what is the difference between Tn and Tp? I will tell you. I will tell you now itself. What is the difference between Tn and Tp? Okay. For some reason this got generated here. That is bad. This won't let me come here actually. Yeah, this will be okay. That is bad. It's some weird bug this currently this is having actually. Sorry, just hold on, give me a minute. Okay, this won't let me do it. Okay, so some weird bug we have. Okay, so where is it? So what I can say is, if I just take the example of this case, right? If I just take the example here, I have already told you what is my TP. Let's say my number of tasks is 10. If n is 10, okay. Let's take example. N is 10. So if n is 10, then what will be my T execute for a pipeline system? How many stages I have? 4 stages. Stage 1, stage 2, stage 3, stage 4. 4 stages I have, plus n, total number of tasks is 10 minus 1 into cycle time, pipeline cycle time. So what should be the ideal? Obviously you can choose higher cycle time than this, but you cannot choose lower cycle time than this. This is a minimum 8 nanoseconds that you have to at least give for all the stages to completely perform properly. You can choose higher, you can choose 10 nanoseconds, that's fine, but your system will be slower. So obviously we'll choose the minimum best one, 8 nanoseconds. So pipeline cycle time will be 8 nanoseconds. So this is actually 13 times 8. So that is 24 and 10. So it is 104 nanoseconds. Okay, for the pipeline system. Now if I have a non-pipeline system, same example, n is equals to 10. What is my Tn now? What is the definition of Tn? Definition of Tn is the time taken to perform single task for a non-pipeline system. So what will be the time taken to perform a single task, right? The stage 1 will take 5 nanoseconds. So after 5 nanoseconds, I can directly go to stage 2 because it doesn't have any foundation that stage 2 is currently performing some other task. No, everything is independent. Everything is happening sequentially. So I can, after doing this operations, fetching the instruction, I can directly give it to stage 2 because it is ideal. It is already free. Everything, only one stage works at a time. So this stage 1 has happened. So 5 nanoseconds has gone and instantly I gave it to the stage 2. Then after 8 nanoseconds, then again I instantly gave it to stage 3. So total how much time I consumed? 5 plus 8, 30 nanoseconds. Then this consumed total 19 nanoseconds. Then again I instantly gave it to the stage 4, that is, it will again consume 4 nanoseconds. So how much time I will take? It will take total 23 nanoseconds. So each instruction takes 23 nanoseconds, and after that, after finishing only this, again I will give the next instruction. It will again fetch that. So each instruction takes 23 nanoseconds. 23 nanoseconds. Each instruction takes 23 nanoseconds, remember. So how many, and they totally independently do the computation, right? So how many number of instructions I have? 10, right? So total execution time will be what? Tn non-pipeline execution will simply be 10 times 23 nanoseconds. It will be 230 nanoseconds. So I hope you have understood the difference between Tn and Tp. It is not necessarily true that always my Tn will be equal to Tp. As we go along, as we move along the subject, you will understand that sometimes Tn is equal to Tp, and then there only the confusion arises. The Tn will always be equal to Tp. No, it will not always be equals to Tp. Tn is not equal to Tp in most cases. Sometimes they will be, but most cases they will not be equal. Okay, so I hope you have understood the difference. It is taking me 230 nanoseconds and this is taking me only 104 nanoseconds. So half the time. I am saving 50% of the time. So there is a metric to compute how much time am I saving. So that is what is my speed up ratio. Okay, so this should be speed up ratio actually. Speed up ratio is nothing but the ratio of two execution times of a non-pipeline system over a pipeline. So what it does is it measures by how much factor I am faster. Okay, that is what my speed up measures. It's just a metric. It just computes that. What is the difference? So how do you remember which one will be at the top and which one will be at the bottom? Always remember that your speed up ratio will always be greater than 1. Okay, speed up ratio will always be greater than 1. Why? I will explain that. So not always actually, not always. Okay, no, always remember that you want your speed up ratio to be as high as possible. You want your speed up ratio to be as high as possible. If you want your speed up ratio to be high, so the top one, right, should have a higher number. So execution time, right, of a pipeline system, most cases is always lower. So obviously lower number will be at the denominator and the higher number will be at the numerator. So lower number will be at the denominator and the higher number, because execution time of non-pipeline system will always be higher. So now can I derive a formula? No need to remember the formula. Okay, you can always derive the formula for the speed up ratio. So very interesting points will come out here. So first point is, if I want to write my speed up ratio, right, what would be my speed up ratio? It is execution time of non-pipeline system. What is the execution time of non-pipeline system? I have already told you that it is n times Tn. I have already defined what is T and what is N. I will not define here again. And what is execution time of pipeline system? It is K plus N minus 1 into TP. Okay. Remember, this is the actual formula. Okay. This is the formula. This is the main formula. Okay. If you want to remember, you can remember. But sometimes what we do is, our number of instructions is very, very higher than the number of stages. Why? Here only we can see, right? If I have chosen, like here only, here I was choosing number of stages to be 100. Sorry, number of tasks to be 100, and number of stages were merely 3. So very, very high. Generally, that is the most cases what will happen. Is then what we do is we make our n to be very, very higher than k. That is, number of tasks is very, very higher than number of stages. Okay. So if n and k are given, you will use this formula of speed up ratio. If n and k both are given, you will use this. So I will write here, if both n and k are given. Now, if for some reason they haven't given you n or k, then what you will use? Then what you will do? Then what you can do is this. You assume n to be very, very larger than k if they haven't given you n and k. If n is very, very larger than k, right? So what will happen is, this k minus 1 I can ignore. If I am doing 10,000 plus 3 minus 1, can I ignore this 3 minus 1 too from the 10,000? Yes, I can. So basically limits concept, right? So I will ignore this. So then what I will get is my speed of ratio will approximately become ntn divided by ntp, which will be approximately equals to tn by tp. Okay, that is what it will come to. Now, if I have a balanced pipeline system, okay, balanced pipeline system. So I will tell here, for a balanced pipeline system, each stage will take same time or cycles. Okay, so that means what? That means if this is a balanced pipeline system, right? So each stage will take same time. So if this is 5 nanoseconds, all the other will be 5 nanoseconds. So if it is balanced, right? If I want to convert this into a balanced pipeline system, then my S1 stage 1 will be 5 nanoseconds. Just a assumption. Stage 2 is 5 nanoseconds. Stage 3 is 5 nanoseconds, and stage 4 is also 5 nanoseconds. Now, if all the stages are 5 nanoseconds only, then what can I say? Then what will be my Tn? Tn is basically sum of all the stages, right? Time of all the stages. Sum of time of all the stages from I equals to 1 to I equals to k. If it is a balanced, right? If it is a balanced, then each stage time period is what? This is also known as TP, right? This is also known as the TP. As it is balanced, it will also be called as TP. Everything is same. So I will choose TP to be this 5 nanoseconds only. Correct? So this can be written as simply TP plus TP plus TP k times, right? K times. This will be equals to what? K times TP. Okay? This becomes K times TP because TP is same and it is a balanced system. Only valid for a balanced system. So my Tn actually will become Tn. Generally the formula for Tn is, here I will write the formula. I will write everything at once here. Formula for Tn generally is basically the whatever I have written at the top, that is sum of the time taken of all the stages. Okay, and I equals to 1 to k. Okay, k is the number of stages. But if Tn is also not given, right, then what we can write is, for a balanced system, I told you this. So for a balanced system, my Tn will become what? My Tn will become what? My Tn will actually become K times Tp, just proved at the top page. Okay. So what will be my speed up ratio? What will be my speed up ratio? So my speed up ratio will become S. It was NTN divided by NTP. NN gets cancelled and Tn is equals to K times Tp, right? Tn is equals to K times Tp. So it becomes, it was NTN divided by NTP and NN gets cancelled. So this is KTP divided by TP. So it becomes K. So my S becomes K. And when will this happen actually? This actually has a name. What is the name of it? The name is S ideal, also known as ideal speed up ratio. Okay, ideal speed up ratio. So this is not ideal pipeline time, this is ideal speed up ratio. So this is ideal speed up ratio, right? What does it mean? What does it signify? If my n is very, very large, then obviously the number of total execution time, right, will almost be equivalent to n only, n cycles only. It will not be equals to n plus k minus 1 because n is very, very large. So as I increase my n, we reach an ideal state where it is like the number of cycles taken will be n plus k minus 1. So that's why it is known as ideal speed up ratio, because we can never reach it. This assumption is, what is the assumption? Assumption is n is very, very greater than k minus 1. That is my assumption basically. So that's why this is known as ideal, because we idealize many things in under ideal conditions only this will happen. And obviously this formula is only valid for a balanced pipeline system. Balanced pipeline system. So sometimes what will happen, GATE will give you question on this. Okay, so the few criteria have to be met, then only you will be able to write your speed up ratio directly equals to k. Else you will not be able to write your speed up ratio equals to k. Assumption is that if I want to say you practically, right, what is happening is the assumption here is that my pipe, right, this pipe is actually already filled. That's why my n is greater. That's what the physical significance of n greater than k minus 1 is. Pipe is already filled, so all stages are already working parallel. Okay, so pipe is already filled, so I am instantaneously getting some output whenever I am giving some input. So that is the assumption that we are telling, that this is my ideal speed up ratio. Ideally this should be the maximum. My speed up ratio, remember, my speed up ratio, actual speed up ratio will always be less than S ideal. Okay, my speed up ratio will always be, just hold on, less than S ideal. So this is how you can verify whether you have solved the question correctly or not. If you're like, you can always compute the S ideal. S ideal will always be equals to k. Also S ideal, right, there can be two ways to go about it. Sometimes S ideal can be equals to this, or S ideal can be equals to this as well. Okay, there are two things here, do remember, can be equals to Tn over Tp. Okay, so remember, like generally we choose this as S ideal only whenever Tn and Tp are given. So if you are able to find out Tn and Tp, how do you find out Tn and Tp? So this you will use when the pipeline is unbalanced. Pipeline unbalanced and TP and TN are given. TP and TN are given. Okay. So what is TP basically? TP generally you will look for the word as cycle time. Cycle time. That is what my TP is. And what is TN? TN is basically sum of the number of stages, right? Each stage, how much each stage time it will consume for I equals to 1 to I equals to N. That simply, not I equals to N, sorry, that I equals to K. That's simply it. Okay. So that is what my TP and TN are. So with the help of this much knowledge, can we solve few questions? So we'll solve the first question, first numerical. A non-pipeline system takes 40 nanoseconds to process a single task. So what does this information give you? It gives me the information about TN. To process a single task, it takes 40 nanoseconds. So TN will be equals to 40 nanoseconds. Next, let's read the question. A pipeline system with 5 segments. Whenever segments, number of segments is given, what does number of segments signify? That is equals to my key. That is equals to 5. And a clock cycle of 8 nanoseconds. Whenever they say clock cycle, right? They say clock cycle. Assume this to be your TP. TP is the like time taken for each cycle to occur. Okay. So clock cycle is this. You will assume this to be TP only. Next is used to process the same task. Okay, it is used to process the same task. Calculate the speed up ratio of the pipeline system for 120 tasks. Additionally, determine the maximum speed up achievable by the pipeline system. That is ideal speed up. Okay. So first I will calculate the speed up for n equals to 120. So formula I know, or I can directly write all the things. What is speed up? Speed up is the execution time of a non-pipeline system divided by the execution time of a pipeline system. What is the execution time of a non-pipeline system? It is n number of tasks into time taken to execute individual tasks divided by what is the total time taken by the pipeline system to execute the same number of tasks. It will be k for the initial task. It will take me k number of cycles plus number of how many tasks are remaining, n minus 1, and how many cycles I will require, same number of tasks. It will be n minus 1 into time taken for each cycle, that is TP. N is simply 120, Tn is simply 40, K is simply 5. It is a 5 segment pipeline system. N is again 120 minus 1 into TP. TP is 8. So this will be 120 into 5 divided by the 124, yeah. Okay. So this will be simply 4 into 30. Okay. 4 into 30 divided by 31 into 5. So what will it come out to be? So I can quickly calculate. Just hold on. Quickly calculate. It will be equals to 30 divided by 31 into 5. So it will be 4 point speed of ratio, right? That I have gotten. It is 4.8387. And what is S ideal? S ideal will be when my number of tasks is very, very high. S ideal is when my n is very, very larger than k minus 1. So S ideal in this case will be simply almost equals, if n is very, very larger than k, right? So this also will be almost equals to n. So it will be Tn by Tp, right? Tn by Tp. So this will almost become Tn by Tp. So Tn is simply what? Tn is 40, right? Tn is 40. Tp is 8 nanoseconds. So 40 by 8 simply becomes 5. So S ideal will always be larger than S, like what do you say, S calculated, right? and this also is equals to the number of stages, but it is not necessarily always this will be the case. This will not necessarily be the case. Here this is equals to number of stages. If S ideal is equals to number of stages, then what we can accomplish from that is it can be a balanced system. It can be a balanced system. I cannot say surely. Why? Because if I have 5 segments, combination of 5 segments, each can be 8 nanoseconds. That is also possible. Or one can be 9 nanoseconds, other one can be 7 nanoseconds, and all the others can be 8 nanoseconds. That is also possible. So it is not always that it will be a balanced system. I cannot comment about that. What I can comment, it can be a balanced system. But if this S ideal is not equals to my number of stages, number of segments, if my S ideal is not equals to K, that is number of stages, what I can comment, I can confirmly say that the system is not a balanced pipeline system, right? It is not a balanced pipeline system. Okay, so that is the important point that I wanted to take away from this. And many educators, they don't teach. Even CS guys, trust me, even CS guys don't know about this. They just know the formula, they just mug up the formula and just put in the question, and their question gets solved, and that's it. They don't understand conceptually what is happening. So there is another term that I have been talking about from the starting of this lecture is throughput. So now we'll understand the definition of throughput. Throughput is what? Throughput is a number of tasks completed per unit time. If you remember, previously I told you that many stages were sitting idle, many segments were sitting idle during sequential execution, okay, of series execution, right? But in pipeline, all the stages are actually happening simultaneously, okay? All the stages are happening simultaneously. So throughput has increased because I am performing more number of tasks in the same amount of one single cycle. In single cycle in pipeline, I was doing 3 things, right? That making of bread example. But in sequential, at a particular time per unit of time, I am only performing one task. Okay, everything is happening series. So in case of a pipeline system, what can I say about the throughput? Can I talk about any formula? Yes, I can. Obviously, you can formula everything, but basic definition you should know. This much is enough. Then you can derive the formula in the examination hall as well. It is equals to number of tasks by total time. So how many tasks am I accomplishing in time? So let's say I am performing n number of tasks. N task. I am performing n tasks. And what is the time taken to perform this n task? It is, if you remember, it is k plus n minus 1 into TP. So just taking the ratio will give me throughput. That's it. So if I just take the ratio throughput, it will be n tasks divided by total time taken, that is k plus n minus 1 into TP. So that is throughput. You can derive a formula or it's totally time fine, right? Now assumption is if my n is very larger than k, right? If n is very larger than k, again I can ignore this k minus 1 here. This will become n by n into TP. So overall this becomes what does my throughput become? Throughput becomes 1 by TP. That is what is written in the next page actually. Okay, here I have added extra pages that are actually not required. So that is what is written over here. If my n is very larger than k minus 1, then my throughput becomes 1 by TP. That's it. Okay, that's it. Basic information that you should know. But basic definition of throughput you should know. That's it. From there you can derive this formula. No issues. Okay. So what are the factors that affect my speed up? There are many things that can affect my speed up, right? So first thing is hazards, like data dependency, control dependency, or structural issues can reduce speed up. We'll understand hazards after understanding synchronous pipelining. Okay, we'll understand this. Don't worry. What are hazards? We'll understand. But that they can affect my speed up. So we want our speed up to be as near as ideal speed up, right? We want it, but sometimes this can cause the speed up to be lower. Basically, overall, it causes the execution time of pipeline system to be more higher. Okay, uneven stages increases the cycle time, lowering the throughput. So if I have uneven stages, right? If I have uneven stages, so what will be my pipeline cycle time? Pipeline cycle time will be the maximum of everything, right? So what is happening here? My TP, I know my throughput is inversely proportional to TP, and my TP is what? My TP is the maximum of times of all the stages, right? Stage 1, TS2, and so on. So obviously, if I have uneven stages, and like if let's say stage 1 is 7 nanoseconds, and the stage 2, all the other stages is 3 nanoseconds. So just due to this single stage 1, I have to give the cycle time. I have to give all the other stages as well 7 nanoseconds. So the number of tasks that I am performing per unit time, per unit cycle time has reduced now, because TP has increased. If TP increases, my throughput will reduce as it is inversely proportional. Okay, that is the basic thing that we wanted to talk about here. Setting up the pipeline and managing tasks introduce delay or overhead. So doing all these things, right? This also is a headache, because you have to manage the tasks, and sequentially there can be few hazards. What type of hazards? To manage those hazards also, it will cause some delay, and those delays are known as overheads. Okay, we'll understand what delay they can cause and what type of problem is there in pipeline processing. Obviously, if you are getting so many good stuff, there will be some disadvantages. Everything has some advantage and disadvantage. It depends what advantages you want and what disadvantages you don't want. Okay, then you choose that particular architecture. How do you optimize? Adjust the design so that no stage is significantly slower than the others. Okay, so all the stages are balanced, because here I just showed you one case. If stage 1 is 7 nanosecond and all the other stages are 3 nanosecond, just due to the stage 1 I have to provide 7 nanoseconds to all the stages. So all the other stages will set ideal for 4 nanoseconds. That is waste of so much time. So we don't want our stages to be unbalanced. We want them to be balanced. Use parallel techniques to handle bottleneck. We'll understand this later on. Don't worry. We incorporate techniques like super pipelining or dynamic scheduling to optimize performance further. So this is not in our syllabus. These are just few theoretical points that you should know. Okay. Main thing is we have to balance the stages. That is the main thing. Now there is another term known as latency. Now what is latency? Latency is the time required to process a single task. How much time does it require to process a single task? So my assumption will be that I am calculating this latency when my pipe is fully filled. What does it mean? That means I will write here, I am calculating the latency when my pipe is fully filled. So what is this? This means technically what does it mean? It means n is very greater than k minus 1. N is very greater than k minus 1. Okay. So if n is very greater than k minus 1, how much time does it require me to process a single task? If I go back to our starting example, if I go back here, right? What was you observing? After, even if n is not very greater than k, right? Then also it will work. After every cycle, I am getting the output of a single input, right? After each cycle, I am getting output. So how much time it required me to process it a single task? One cycle. After each cycle, I am getting output. So after each cycle, I am getting an output of the task. The task has been completed. So how much time did it take me? One cycle. Okay. So latency will be one cycle. So if my n is, even though if my n is not very larger than k minus 1, then also it is okay, right? So just not very large. Okay, just my pipe has to be fully filled. When my pipe gets fully filled, when my n is greater than k minus 1, that's it. After fetching the first instruction, right? After fetching the first instruction, it's done. It is done, correct? So that's it. So latency for a pipelined system, right? Latency for a pipeline system it will be simply TP. But what about latency for a non-pipeline system? To process a single task, how much time is it requiring me? Okay, it is requiring me n times Tn, right? Not n times Tn, so Tn, because each task takes n Tn time. So for a non-pipeline system, the latency will be Tn. For a pipeline system, the latency will be Tp. So you can write the speed up as a ratio of latency of non-pipeline to the latency of a pipeline system. Okay, so you can write that as well. So now you can come to synchronous pipeline. What is synchronous pipeline? It is nothing but what we have studied. That's it. Just it has a name known as synchronous pipeline. So synchronous pipeline is a type of pipeline where all the stages are synchronized to operate using a common clock signal. So what we do is we choose a common time period for each stage, right? What we are doing? We are choosing the maximum time, right? For each stage, like I'm just computing the time taken by each stage, and then I'm choosing the maximum out of those stages. I'm choosing a common time, right? So that is what it is doing. It chooses a common clock signal, that is a common time. So TP. But generally what we do is, in synchronous pipeline, TP is the maximum of time of all the stages, correct? Each stage of the pipeline performs its operation in a fixed time interval known as the pipeline cycle time. So like, although we have already known it, okay, I've already solved a question using this concept only, that pipeline cycle time. So each stage will complete its task within the pipeline cycle time. Okay, each stage completes its operation within the pipeline cycle time. Registers are placed between stages to temporarily hold data and maintain synchronization. So we place registers here, okay, as explained in the starting slides as well. If you have seen, there were registers. What they do, they just store the data, because actually internally what will happen, this stage, right, will finish the task, let's say very earlier, let's say in 2 nanoseconds, but my pipeline cycle time is 5 nanoseconds. So we don't want to keep that data here. Whatever result it has done, we don't want to keep it here. We want to store it in some register. From there we will take it. Okay, so the data is will get stored as a register at 2 nanoseconds, and then I will wait, and then finally at 5 nanoseconds this data will be given to the next stage. Okay, so that is what we do. This is also known as this intermediate like buffers. Okay, registers are also known as intermediate buffers actually. Intermediate okay, this registers add a small delay, because obviously I'm storing the data, then again I'm sending it back, so this will cause some delay. That is also known as a register delay. That will be included. This will be included in the pipeline cycle time. So our TP after this register delay, our TP will be what? This will be equals to maximum of each stage time, whichever will be the highest, plus the register delay, obviously. That we have to consider, because let's say one stage takes 7 nanoseconds. All the other stages take 3 nanoseconds only. One stage takes 7 nanoseconds. It will have some also delay, right? To store it in data, then again to take it back from the register. So let's assume the register delay is very small, 1 microsecond, or it's generally very small. Okay, so we will add it. So our final cycle time TP will be maximum of this plus the T delay. So just this thing that you need to keep in mind. Okay, so That is what we do. So why are buffers required? So I have told here as well that the buffers are required to synchronize. That is the task of synchronous pipeline, right? Buffers are used to synchronize the pipeline stages. They store the data, hold the data, then again when it is required for the next stage, they give it back. So synchronization. I can write here simply synchronization. Okay, of the pipeline system. Okay, so just remember, they will only be used in a pipeline system. Buffers will not be used in a non-pipeline system. Buffers will not be used in a non-pipeline system. Why? Because the reason that we kept buffer was to synchronize everything, right? That was the main reason that's why we used buffers. Synchronize what? Synchronize stages from pipeline. But in non-pipeline system, we don't need synchronization, because as soon like each task is operating separately. We don't like my stage 1 is not doing some task and performing some task, and then again at the next clock cycle stage 2 is performing some task, and like stage 1 is also performing some task. It doesn't happen in non-pipeline system. In non-pipeline system, only one stage performs a task in a complete cycle. All the stages don't perform, so it's okay. We don't need a buffer to temporarily hold the data and then give it back to the next stage. What I do, as soon as I perform some task in the stage 1, I instantly give it to the next stage. I don't need to hold and then give it back to the next stage, because the stage 2 at that point of time is not doing anything. It is just idle. It is waiting for the stage 1 to give it to something. So it's totally fine. It's totally fine, right? So we don't need any registers or buffers in a non-pipeline system. That is the important point that I wanted to tell you here. Okay. So like what was the formula? General formula for TP. Just remember these two things. TP, it will be maximum of all the segment delays, whichever one is maximum, plus my delay of the register, buffer delay. I can write this better. Buffer delay. Okay. And what will be my non-pipeline time? Non-pipeline time will be summation of all the segment delays. So let me take an example here. So if let's say I have 4 segments, so k is equals to 4 and ts1 equals to 2 nanoseconds, ts2 equals to 3 nanoseconds, ts3 equals to 4 nanoseconds, and ts5 equals to 1 nanosecond. Okay, and my buffer delay this is not ts5, sorry, this is ts4. Buffer delay TBD is equals to 0.5 nanoseconds. So what will be TP here? So my TP, like here also, okay, I have already given an example here. Okay, this example was already there. Anyways, okay, We had 1, 2, 3, 4, 3 stages. I can give this. I will take this example. So here, what will be my TP? TP will be maximum of all the segment delays. That is this 3, 4, 1, and 2. What is the maximum? Maximum is this, right? 4. So it will be TP will be equals to, in this case, TP will be 4 nanosecond plus obviously the buffer delay will be there to synchronize everything. 0.1 nanoseconds. So it will be 4.5 nanoseconds. What is my TN here? TN, right? I don't need buffer here. I don't need buffer. Now you might say, why am I not adding buffer delay for all of the stages? TP is what? TP is the cycle time of one stage, right? So that's why in one stage only one register delay will be present. That's why we only add it once. In TN, I need to add all the segment delays, but I will not include buffer because for a non-pipelian system, we don't have buffer. So just I will add all the segment delays. So it will be 2 plus 3, 5 plus 4, 9 plus 1, 10. So it will be 2 plus 3 plus 4 plus 1 equals to 10 nanosecond. That's it. That is how you compute TP and TN. Okay, I hope you understood this point. Your TN will always be sum of all the segment delays. Excluding this, I should write excluding the register delays obviously. So we, for a non-pipelian system, we will not use registers. Okay, this is the important point that you should know. Okay, so yeah, that is what is here. That is what my synchronous pipeline is. Okay, so one more thing is that if the system is balanced, then my TN will be equals to what? TN will be equals to KTP if all segments are balanced. Balanced meaning all segments have same segment delays. Pipeline balanced, all segments have same delay. And just one more information, if you are using a pipeline system and there is register but they haven't given the delay of the register, then what you will assume? You will assume register delay to be 0 if nothing is mentioned about the delay, right? You assume it to be 0. Generally it is very low. Okay, so what I wanted to do is do few questions. So I wanted to do a few questions, and in then like after you take the screenshots, okay, you try to attempt and tell me your answers in the comment below. Write down in the comment below your answers and tally your answers with my answers. This is the first question. This is the second question. Third, then this is the fourth one. Just take a screenshot and try to attempt and then tally your answers with mine. Okay, fourth, this is 72nd, right? Yeah, fourth, then fifth, then sixth, then seventh, then 8, then 9. Okay, this is the last one, 8 one. Okay, you try to attempt all the questions and now I will come back with all the solutions. Let us do this first question. So we have a 5 segment pipeline with segment delays 8 nanosecond, 10 nanosecond, 7, 9 and 11. So I will write that down, that my K is equals to 5 and my TS1 is 8 nanoseconds, my TS2 is 10 nanoseconds. Okay, just hold on. TS2 is 10 nanoseconds, TS3 is 7 nanoseconds, TS4 is 9 nanoseconds, and TS5 is 11 nanoseconds. Okay, so what we have to we have to determine the total processing time for 800 tasks. So here my n is equals to 800. Using the pipeline system, also calculate the speed of the pipeline as compared to the corresponding non-pipeline system for same number of tasks and compare it with the ideal speed up. So first of all, I will calculate the execution time of a pipeline system. T P execute. Correct. So this will be equals to what? This will simply be equals to, like I already know that to perform the first task it will take me k cycles. To perform the other n-1 task it will take me n-1 cycles into TP. So what will be TP here? They haven't not mentioned register. So my TP will be equals to max of TS1, TS2, TS3, TS4, or I can directly write it instead of doing this: 8, 10, 7, 9 and 11 nanoseconds plus the delay of the register, but no delay has been mentioned, so I will assume it to be 0. So my TP will be maximum of this, that is 11 nanoseconds. So what will be my execution time? It will be k is 5 plus 800 minus 1 into 11. So it will be 804 into 11. So it will be 8844 nanoseconds. Okay, or this can be written 8.844 microseconds. Now what about the non-pipeline system? If I have a non-pipeline system, how much time it will take me to execute the same number of tasks? So T NP, capital NP EXC, it will be simply n times Tn. Now what is Tn? Tn will be sum of all the stage delays, right, or the segment delays. It is 8 plus 10 plus 7 plus 9 plus 11 nanoseconds. So this becomes 20 and this becomes 25. So this becomes 45 nanoseconds. So n is how much? 800 into 45 nanoseconds. So 45 into 800, this is 36 000 nanoseconds, or I can write 36 microseconds, right? And what is the speed up? Speed up ratio S will be simply higher by lower, right? So higher, what is higher? Higher is 36, that is n non-pipeline execution time divided by the T pipeline execution time. Okay, so this will be equals to 36 micro divided by 8.844 micro. Everything is in microseconds. So this will be into almost equals to 4.07. okay, this is the speed up ratio. This is the actual speed up achieved. Now what is the ideal speed up ratio? As ideal, right, will be when my n is very greater than k minus 1. So then what will happen is the speed up will approximately be equals to Tn over Tp. So it will be approximately equals to Tn is how much? Tn is 45 and Tp is 11. Correct? All this in nanoseconds. So it will be 45 upon 11. So this will be 4.09 ratio. Okay, so our ideal is this. We are very close to our ideal, but it is not greater than that. So obviously we cannot go beyond our ideal speed up ratio. So I have compared my ideal speed up and like speed up achieved. Okay, this is also a term known as pipeline efficiency. Pipeline efficiency is speed up achieved by speed up ideal. Okay, how much closer I am to my ideal speed up. Okay, so the pipeline will be more and more efficient. Let's do the next question. So in this question we have the following 4 processors. Assume that the pipeline register has 0 latency, basically they don't have any delay. Then which processor has the highest clock frequency? What is clock frequency? What is clock frequency? Clock frequency, if you remember, f clock is basically 1 by clock time period, right? 1 by t clock time. Frequency is just the inverse of time period. What is t clock? T clock is the TP, right? Because it is known as the cycle time of the pipeline cycle time. So they are telling me which one has the highest clock frequency. So they are asking me which one has the highest clock frequency. That means which one has the lowest clock time period or the lowest pipeline time. Okay, so which one has it actually? So obviously my pipeline time, how do I determine the pipeline time, pipeline cycle time? I choose the maximum of all the stage latencies. Latency meaning delay. So here for the TP1, what will be my cycle time? TC1, it will be what? It will be maximum of all of this, that is maximum is 2 nanoseconds. Here as well maximum is TC2 is 1.5 nanoseconds. Here as well maximum how much? It is 1 nanoseconds. TC3 is 1 nanoseconds. Here maximum is 1.1 nanoseconds. TC4 is 1.1. Now out of this 4 I have to choose the minimum. Which one is the minimum? This third P3 processor. So here like it's very simple, right? Very simple. Don't do it using very difficult maths or something. Processor 3 will have the peak clock frequency. Okay, as its time period is the lowest. Okay, so let's move on to the next question. These are all very simple questions. You also will be able to solve it. So here we have like a instruction pipeline with 4 stages, each with combinational circuit delay. So each stage has delays. Okay, and also it has a pipeline register which delays 1 nanosecond. They are provided as a delay. So now the delay comes into the factor. Okay, now each stage has like separate delays. Okay, so what are they asking us? The pipeline registers are required between each stage, and at the end of the last stage, delays for the stages at the end of the last stage, delays for the stages and for the pipeline registers are given as what? Are given in the figure. What is the approximate speed up of the pipeline in steady state under ideal conditions compared to corresponding non-pipeline implementation? Okay, very interesting question. They're asking me steady state under ideal conditions when compared to non-pipeline implementation. So in nowhere they have given me the number of instructions or number of tasks. So what I will assume? I will assume, obviously they are telling me ideal, so my assumption will be n will be very greater than the number of stages or segments. Okay, so what does my speed up ratio then become? My speed up, if you remember it very well, if you don't remember, you can directly write it is the execution time of non-pipeline system over a pipeline system. What is the execution time of a non-pipeline system? It is n times tn. I can write directly as well. It will be tn times tp, but still I want to write it in front so that you don't think that I am just mugging up the thing. Okay, so it is k of a pipeline system. What is the execution time? K plus n minus 1 into tp. So this my n is very higher than k. N is very higher than k minus 1. Okay, so if n is very higher than k minus 1, then my ideal speed up approximately becomes tn over tp. Okay, it approximately becomes tn over tp. So we have to find out tn and tp. So first let us find out tp. That will be the easier one. tp will be what? TP will be maximum of all the segment delays. Okay, so this is 5, 6, 11, 8. So 5, 6, 11 and 8, plus obviously I have taken into consideration the register delay. Now register delay will not be different because it's the same register, right? It is not doing something different. It is just storing the data, capturing the data. So register delay will be same because it is doing the same, performing the same task. But few instructions may take more amount of time to decode. Few instructions may take less amount of time to decode. So that is different. That can be different, right? But register delay will be same. It will not be different. So register delay is 1 nanosecond. So all this is in nanoseconds. So maximum of 5, 6, 11, 8, that is 11 plus 1. So it becomes 12 nanoseconds. So it becomes 12 nanoseconds. So my TP actually becomes 12 nanoseconds. What about TN? What will be TN? So TN is basically the time taken for me to perform one instruction for a non-pipeline system. I have told you for a non-pipeline system, I will not consider register delays because for pipeline system only we need registers. For non-pipeline system, there is no requirement of registers, right? Explanation has been provided at the starting of this lecture. So TN will just be the summation of all the delays, right? So it will be sum of 5, 6, 11, 8 nanoseconds. So this will be 5, 5, 10 and this is 11, 11, 22, 30. So this will be 13 nanoseconds. Okay. So my S ideal, right? S ideal will be what? Ideal speed up. It will be TP upon TN. So this will be equals to 12 by 30. So this will be 4 by 10. Okay, I am wrong actually. This is the opposite, right? Sorry. It's the opposite. It's TN over TP. Higher over lower, right? It cannot be lower. So it will be 30 over 12. So this will be 10 divided by 4. This will be 2.5. So ideal speed of achieve will be 2.5. This will be your answer. Okay, very simple. Like these questions are very, very simple actually. These questions are very, very simple. And let's solve the next question. So in the next question, what have they told me? They have told, given the stage delays, okay, in a 4-stage pipeline, that is 800, 500, 400, 300 picoseconds. So stage delays are given. It is a 4-stage. So as soon as you read the question, right, you write down the information. So my K is 4. My stage delays are 800. So my TP will be what? TP will be maximum of 800 plus 500. No, sorry, plus, not plus, comma 400, comma 300 pico seconds. Okay, so the first stage with delay 800 picoseconds is replaced with a functionality equivalent design involving 2 stages with respective delays. The first stage is replaced, that is 800 picoseconds, with a functionality equivalent design involving 2 stages. So this 800 picosecond, right, stage 1, this has been further divided into 2 stages. Why? We'll understand why we do this. Okay, one to 600 picosecond, another one to 350 picosecond. Now you might say overall it is consuming more time, 950 picoseconds, but actually it can actually increase our throughput. What is throughput? Throughput is the increase of the instructions executed per unit time. Okay, so how it will increase the throughput? So very simple, right? Very simple. What we are doing is, in case 1 where I didn't break down anything, right, I had 4 stages, right? This was 4 stages, 1, 2, 3, 4. Okay, so K was equals to 4 in case 1. And what is my TP? TP will be this, right, maximum of this, that is 800 picoseconds or 0.8 nanoseconds. Nothing has been mentioned. Registers have not been mentioned. I will assume it to be not there. What is my throughput? Throughput is 1 by TP. Correct? Or like you can write n minus k, that formula you can do, but generally like you can understand throughput is instructions executed per unit time. So in a single cycle I execute instructions, so it will be throughput will be 1 by TP, 0.8 nanoseconds. So this will be 1 by 0.8. Okay, this will be my throughput in the case 1. In the case 2, what is happening? In the case 2, what is happening? In the case 2, my through k number of stages has, like I have further divided this into 2 stages, right? So overall how many stages I have? This has been gone. This is this. So total 5 stages I have. K is equals to 5. And what is my TP? TP now will be maximum of 600, because I have further divided that into 2 segments, right? 350, and the others are same only. This 500, 400 and 300. 500, 400 and 300. Okay, so these are same. Okay, so this will be equals to, now what is my TP? TP is 600 only, right? This is my TP2, this is my TP1. 600, not nanosecond, picosecond. So this is in picoseconds. I can directly write it in nanoseconds. So it will be 0.6 nanoseconds. So my TP2 will be equals to, my TP2 will be, this is TP1, it will be 1 by TP2, right? So that is 1 by 0.6. Now they have asked me what is the percentage increase in throughput. Obviously this TP2, right, has reduced. If TP2 reduces, the throughput reduces. Okay, or this is also a formula for clock frequency. Okay, you can also say throughput is a formula for clock frequency. That also you can say. Okay, so what will be the percentage increase or change in throughput? It will be TP2 minus TP1 divided by the old, that is TP1, into 100. So this will be equals to how much? This will be simply 1 by 0.6 minus 1 by 0.8 divided by 1 by 0.8 into 100. Remember, all this is in, like this is nanosecond, so this will be in what? Gigahertz, right? Gigahertz. So just remember, but as we are calculating in like unitless, because there is a throughput in the denominator and numerator as well, so units will simply get cancelled. So what it will become is this, right? So this will become 8 by 6, that is 4 by 3 minus 1 divided by the 1. So it becomes 1 by 3 into 100 simply. So it becomes 33.33%. So the answer will be 33.33, because they have asked in percentage only, by how much percent throughput increases. So obviously that is the advantage. I'm able to do more tasks. Okay, because TP has reduced. Previously I was not, like this stage was taking so much time that there was more idle time here, right? Because I was giving 800 seconds for each stage. So this stage also got 800 seconds, this stage also got 800 seconds. So the maximum idle time for a particular, for all the stages, like I'm just choosing the maximum one, is here in this case it is 500 picoseconds for this last stage, right? But if I break it down, the first stage, if I break down the first stage, then what is the maximum idle time? The maximum idle time then becomes, this is the case 1, and in the case 2, the maximum idle time, now what is my TP now? TP is 600 now, it is not 800 anymore. So maximum idle time can only be 300 picoseconds, right? because I have given 600 picoseconds for this particular stage, but it doesn't require 600 picoseconds. It only requires 300 picoseconds. So obviously it will only take 300 picoseconds. That's it. Okay. So that's very simple. That's very simple. That's why the idle time of the maximum idle time has reduced. So obviously the throughput will increase because now they will execute more tasks. Okay. In a per unit time, they will execute more number of tasks. So that is the importance of throughput basically. Okay. So let's do the next question. So in the next question, we have a non-pipeline processor with a clock rate of 2.5 gigahertz. So what does it mean? Okay, we will understand that later. The non-pipeline processor has a clock rate of 2.5 gigahertz. F clock is 2.5 gigahertz. And average cycles per instruction of 4. Okay, so I hope you know what is average, like CPI. CPI is what? CPI average they have given me as 4. Okay. So from this, can I say how many cycles does each instruction take? Okay. So or what is a TP basically? Or what can I say? Cycle, like F clock is this. This can be written as what? This can be also written as cycles per second, right? That is the definition of frequency, cycles per second. And they have told me how many cycles each instruction take. So can I, from this information, can I find out the total time of each instruction for a non-pipeline processor, that is TN? What will be TN equals to? TN will be equals to CPI average, that is the number of cycles per instruction. Okay, because I need to find out the execution time of a single task, of a single instruction. So number of cycles I have got into the time taken by each cycle, or T cycle. What is T cycle? T cycle is just the inverse, right? T cycle will be just the inverse of this. That is, T cycle will be 1 by F clock simply. Okay, so this will be 4 times 1 by 2.5 gigahertz, or this will come out to be nanoseconds because giga is nano. Okay, so this will become what? This is 4 by 2.5. I can multiply this by 2 by 8 by 5 nanoseconds, or 1.6 nanoseconds. So this is my TN actually. For a non-pipeline system, this is the time that it is consuming. Next, but due to internal pipeline delay, okay, so sorry, the same processor is upgraded. Now it is upgraded to a pipeline processor with 5 stages. So I have upgraded this non-pipeline processor to a pipeline processor with 5 stages. So my K will be 5 simply. Next, what they're telling me? They're telling me, but due to internal pipeline delay, the clock speed is reduced to 2 gigahertz. So for some reason, due to registers or anything, the clock speed, F clock P has now reduced to 2 gigahertz. Okay, it has now reduced to 2 gigahertz, right? Just hold on. Yeah, everything is fine. 2 gigahertz, right? So from this information, can you tell me what will be the TP cycle time? It will just be the 1 by F clock, right? This I have told you why this will be like this. I have already told you at the starting of the today's lecture, right? So it will be 1 by 2 nanoseconds, or 0.5 nanoseconds. Okay, so that is the case over here. So obviously my TP will change, things will change. Now what are they asking? They are asking me, assume that there are no stalls in the pipeline. Just ignore this line. What is stalls? Stalls comes due to hazards. Just ignore this line. It's not important. The speed up achieved in this pipeline processor. What is the speed up achieved in this pipeline processor? So speed up will, what is the formula for speed up? It is T execution of a pipeline system, sorry, non-pipeline system, over the T execution of a pipeline system. So this is equals to what? How do you calculate? Now it has also asked me the speed up achieved, but they have not told me the number of tasks. So if they have not told me the number of tasks, what can I assume? I can assume that my n is very greater than k minus 1. They have not told me. So then what does my speed up become? I have done this, like I have defined this, derived this many times in this lecture. So it will be directly Tn over Tp. So what is my Tn? Tn is simply 1.6 nanoseconds, right? And what is my Tp? Tp is simply 0.8 nanoseconds. So not 0.8, sorry, 0.5 nanoseconds. So your speed up achieved will be 3.2. Okay, you can clearly see that your like if I break this down, right, how many number of stages I have? 5. So if I do k times Tp, right, k times Tp is 5 times 0.5, that is 2.5 nanoseconds, which is not equals to Tn. So it is not a balanced pipeline system. Okay, it is not a balanced pipeline system. So I hope you understood. Like I went a bit fast, but I hope like everything is simple, right? Just you have to find out the Tn and Tp, because here they have not mentioned me the number of tasks. So I'll assume n to be very high. If n is very high, then my speed up changes to ideal speed up, that is Tp over Tn. Okay, if they would have told me that it is a balanced system, then it would have been, speed up would have been equals to k, but it is not. Always remember this formula. If you want to remember anything, always remember this formula only, because if it is a balanced system, automatically this will get converted into k. Why? Because your Tn will automatically be equals to k times Tp. Tp will get cancelled and you will be left with k only. So if you want to remember, you can remember this formula. That's enough. Okay. So I hope you understood this point, and this is also very important point, that for a non-pipeline system they have mentioned the clock frequency. So it is the cycles per second. Okay, and each instruction takes 4 cycles. So overall, how much time will each instruction take or each task take? That is 1.6 nanoseconds. For pipeline, how much time will each task take? If n is very larger than k minus 1, obviously each task will only take 1 cycle. Why? Because after every cycle I am getting an output. Something is coming into the pipe and something is going out of the pipe every instant. Okay. So that's why each cycle will take Tp amount of time. So Tn over Tp will be 3.2. I hope you understood this point. Let's do this question. Comparing the time T1 taken for a single instruction on a pipeline CPU. Okay. T1 is the time taken for a single instruction on a pipeline CPU. So what will be my T1 equals to T1? If I am only doing a single instruction, so n is 1. So simply it will only take k times Tp, right? Comparing with time T2 taken on a non-pipelined but identical CPU. What does identical CPU means? Identical CPU means they have same clock frequency. You have bought CPUs, right? You know few specifications of CPUs. This is a 3.2 gigahertz CPU, AMD Ryzen 3.2 gigahertz CPU, or like your chips. Phone chips has 3.2 clock speed, 3.2 gigs of clock speed, or 3.4 gigs of clock speed. What is it? It is CPU, right? So if it is same CPU, the clock speed will be same. Now, if the clock speed is same, that is their F clock is same. That is their T cycle, right? Cycle time is same. Cycle time is same. Okay. If the cycle time is same, then what are they asking? They are asking, what can we say? So this, right, T1 will become what? T1 will become k times T cycle actually. What can we say? T1 will be less than equals to T2. T1 will be greater than equals to T2. T1 will be less than. How can I say this? Okay. So what you can do, you can assume few cases here. So if I assume few cases, let's take like a 4-stage pipeline system. Okay, these are 6, 7, 8 and 9. Okay, just assume any number. 6 seconds also you can assume. I'm assuming any number. And let's take another case that is all balanced. And again I have 4 stages and all of them has 4 seconds of segment delays. Now, how much will this one take? How much will this one take? Its TP will be what? TP will be 9, right? So my assumption is clock cycle is this. So the clock cycle will be decided by TP only. TP will be here, in this case TP will be what? Maximum 9, assuming no resistors. But what will be TN actually? TN, right? TN will be 6 plus 7, that is 13 plus 8, that is 13 plus 8, 13 plus this 13 plus 8, 21, 21 plus 9, that is 30 nanoseconds. Okay, or 30 seconds, anything. But what is my time? Execution time of a pipeline system. Execution time of a pipeline system for a single instruction, it will be K times TP, that is 4 into 9, that is 36 nanoseconds. So here I can observe that execution time, that is, this is my T1, right? T1 is greater than T2. And here, if it is a balanced system, right? If it is a balanced system, here what will be my TP? TP will be 1. TN will be what? It will be sum of all the stages delays, that is 4 nanoseconds. What will be my T execution of pipeline system? This is my T2, right? TN is simply my T2 because I am only executing a single instruction. That's why. T execution here will be simply K times TP. I have 4 segments, so it will be 4 nanoseconds. So here my T1 is simply equals to T2. So for a single instruction, what I can say is, for a single instruction, my T1 will always be greater than or equals to T2. So option B will be correct. Mathematically also we can prove, right? So what is my execution of a non-pipeline system? Non-pipeline T execution of a non-pipeline system. Okay. T execution of a non-pipeline system is what? It is simply equals to n times Tn, right? And if it is a single instruction, it will be simply equals to Tn. And this is equals to sum of all the segment delays. So let's say this is T1 plus T2 plus T3 plus T4. And let's assume that maximum out of T1, T2, T3, T4 is T2. Just my assumption. Okay. The same thing, T execution for a pipeline system, it will be for a single, generally the formula is this Kn minus 1 into Tp, but for a single instruction n will be 1, so it will be K times Tp, and Tp is what? Tp is simply T2. It will be K times T2. So this is also 1, 2, 3 K only. K only. So here my K is 4. That is my assumption. So this will be 4 times T2. So what I can observe that this is my T1 and this is my T2. What I can observe is this is 4 times my T2, and I am also adding 4 times here, but not T2 actually, not the highest value. I am adding lower values. So obviously if I am adding lower values, let's say T2 is 30 nanoseconds. Now all these are 10 nanoseconds. So this will become 10 plus 10 plus 10, 30 plus 30, 60, and this will become 4 times 10, right? 4 times 30, that is 120 nanoseconds. So always my T1 will always be higher than T2 for a single instruction. Only for K n equals to 1, remember, only for n equals to 1. So that's why I have chosen option B. So this is only valid, remember, only valid for n equals to 1 instruction. It is not valid else. It is not valid else. Okay. So very simple thing. A 4-stage pipeline has delays this and registers have delayed this 5 nanoseconds. Assuming constant clocking rate, the total time taken to process 1000 data items on this pipeline. Very simple, right? Again, you have to choose the maximum. Basically, TP will be what? TP will be maximum of all this. It will be maximum of 150, 120, 160, 140 nanoseconds plus stage register stage delay. Each stage has 5 nanoseconds of delay. So this will become 160 plus 5 nanoseconds. So this will become 165 nanoseconds. TP will become 165 nanoseconds. Now, assuming the constant clocking rate, the total time taken to process 1000 data items on this pipeline will be. So obviously, it is asking me execution time of a pipeline system. What is it? It is simply equals to KA plus N minus 1 into TP. So how many stages I have from the delay, right? I can see it has 4 stages. So K is equals to 4. 4 plus N. N how many? 1000 I think. It is 1000 data items. 1000 minus 1 into TP. TP is 165 nanoseconds. So this will become 1003 into 165 nanoseconds. So this will, I will just quickly compute this. What have they asked? In microseconds, right? So almost it will be almost equals to 165 micro only. 165.495. So almost equal to this. Option C will be correct. I have just converted it into micro. That's it, right? So these are all very simple questions, and I know you will be able to solve it. So let's take another question. We have two designs, D1 and D2, for a synchronous pipeline processor. Okay, both are synchronous pipeline processor. Only two designs we have. One design D1 has 5 pipeline stages. So my K1 is equals to 5 with execution time. Each stage execution time is 3 to all this, right? So obviously, what will be my TP? TP1 will be maximum of 3 to 4 to 3 nanoseconds. Okay. While design D2 has 8 stages. So K2 is 8 and my TP2 will be what? It has 8 stages, right? Each with 2 nanoseconds execution time. So TP2 will be simply 2 nanoseconds because maximum of 2 nanoseconds of all, each has 2 nanoseconds, right? It will be simply 2 nanoseconds only. How much time can be saved using design 2 over design 1 for executing 100 instructions? So how much time can I save in design 2? Because overall it has 8 stages, right? So each instruction it is taking 16 nanoseconds for the first instruction only. After that it is only taking 2 nanoseconds. So that is the advantage. Here the maximum will be 4 nanoseconds. Correct? So each after the first instruction, each instruction will take 4 nanoseconds to fetch. So how much, what is it telling? How much time can be saved on design T2? So it is asking me to find out T execution in the second design minus T execution in the first design for n equals to 100. So this will be what, like formula is same, right? It is like first instruction K1 minus n, that is n equals to 100 minus 1 into TP1 minus, okay, this should be actually 2, sorry. Yeah. How much time am I saving? How much time am I saving? How much time can we save? So obviously I will write this actually T1 minus T2 because they are asking me how much time have I saved. So T1 obviously will take more time. Design 1 will take more time than T2. So that will give me the amount of time that I have saved actually. So it will be K1 TP1 then K2 minus n minus 1 into TP2. So this will be equals to K1 is 5 minus n. N is basically 100. Sorry, this will not be minus. Sorry, this will be plus. Right? Sorry, plus 100 minus 1. What is TP1? TP1 is 4 nanoseconds, correct? Minus all this is in nanoseconds only. K2 has 8 stages, but it won't matter much because my overall cycle time has reduced, right? It is 2 nanoseconds only. So this will be 104 into 4. So this is 416 minus, this is 214 nanoseconds. So this will be 202 nanoseconds. So total I am saving in the, if I use a design 2, I will save 202 nanoseconds. So sometimes this has disadvantages like breaking it down into multiple stages, but most cases if I keep my segment delays consistent, then obviously I am saving huge amount of time because the idle time has reduced, explained in previous question as well. So how much time have I saved? 202 nanoseconds. These are all very, very simple questions. Okay, so let's do this last question. So we have a 3 GHz processor with a 3-stage pipeline and stage latencies as tau 1, tau 2 and tau 3. So my clock, right, frequency of the clock, f clock, is 3 GHz. Okay, fine. And it is a 3-stage pipeline. So K is 3. And each stage has latency or delay of tau 1. So like the first stage has tau 1, second stage has tau 2, third stage has tau 3. And they have given me the relationship between each stage delays. So this is a very, very brilliant question. Please focus. Please focus here. Okay. So they have told me that tau 1 is actually 3/4 of tau 2 and tau 1 is also twice of tau 3. That is a relationship that they have given me. Now, what are they asking? If the longest pipeline stage, I don't know what is the longest pipeline stage out of this, tau 1, tau 2 or tau 3, they tell me it is split into 2 pipeline stages of equal latency, the new frequency will be. So first of all, first thing is I have to identify what is the longest pipeline stage. Okay, that is my first task. How do I find out what is the longest pipeline stage? So I have tau 1, tau 2 and tau 3, they are related here, right? So it is telling me that tau 1 is 3/4 of tau 2. So obviously my tau 1 will be less than tau 2. Let's take an example. Let's take tau 1 to be 1. Okay, or tau 2 to be 1 nanosecond. If I take tau 2 to be 1 nanosecond, what will be tau 1? Tau 1 will be 3/4 nanoseconds, which is less than tau 2. So obviously tau 2 will always be less because obviously I am multiplying it with a fraction with tau 2. So tau 1 will always be less than tau 1. What about the second? It is telling me that tau 1 is twice of tau 3. So obviously I can say that tau 1 will be greater than tau 3. Why? Just take an example. Tau 3 will be 1 nanosecond. If tau 3 is 1 nanosecond, tau 1 will be twice the 1 nanosecond, that is 2 nanoseconds. So tau 1 will be greater than tau 3. Simple, right? Tau 1 is 1 nanosecond, tau 1 comes out to be, so tau 3 is 1 nanosecond, tau 1 comes out to be 2 nanosecond. It is greater than. So it will be greater. So out of these two inequalities, I can completely see that tau 1 is greater than tau 3 and tau 2 is greater than tau 1. So I can arrange this like this. Tau 2 is greater than tau 1 is greater than tau 3. So my largest segment delay will be tau 2. So obviously that is what my TP will be, right? TP will be what? They have not provided any register delay. So maximum of tau 1 tau 2 and tau 3. Now what is the larger of these three? Larger of these three is tau 2, right? Tau 2 is the highest. So obviously my TP will be tau 2. Obviously my TP will be tau 2 simply. Okay. And I also know f clock. And what is f clock? F clock is simply equals to 1 by TP, correct? So from here I can directly find out my tau 2 and I can find out everything. So 1 by f clock, that is 3 gigahertz or nanoseconds, is equals to tau 2. Correct? I have directly found it out because it is 1 by f clock. Now next what they are telling me? They are telling me if the longest pipeline stage is split into 2 pipeline stages with equal latency. So this tau 2 has been split into 2 stages of tau 2 by 2 and tau 2 by 2. Then what they are telling me? Then they are telling me the new frequency will be. So now this will become what? This will be 1 by 6, 1 by 6. What about tau 1? Tau 1 is 3 by 4, tau 2, right? Tau 1 is 3 by 4, tau 2. So what is tau 2? 3 by 4 into tau 2. What is tau 2? Tau 2 is 1 by 3. It is 1 by 4 nanosecond. And what is tau 3? Tau 3 is 1 by 2 of tau 1, right? Tau 1 by 2. Tau 3 is tau 1 by 2. Tau 1 is 1 by 4. So tau 3 will be 1 by 8 nanosecond. Tau 3 will be 1 by 8 nanosecond. So tau 3 is 1 by 8 nanosecond. So finally, what will be the new TP2? TP2 will be the maximum of 1 by 6, 1 by 6. Like I can write it like this. It will be maximum of 1 by 4, 1 by 6, 1 by 6 and 1 by 8. Because I have broken down the longer stage delay, right, to 2 delays. So TP2 will be what? This will be the highest, right? 1 by 4 simply. So now what will be the clock frequency? This is nanoseconds. F clock will be what? It is the inverse. F clock 2 will be the inverse of 1 by TP2. So it will be 4 gigahertz. Frequency has increased, right? Because obviously throughput also has increased. So answer will be 4 gigahertz. This will be the answer. So very simple question, but elegant question, right? Because many things are unknown. You have to identify the question perfectly and find out the result. Okay. So basically that's it for today's lecture. I hope you have enjoyed today's lecture, and from the next lecture onwards, we'll understand few hazards and a lot more things about instruction pipelining. This was just the introduction and questions on instruction pipelining. Thank you for watching, and I will see you in the next lecture. Until then, happy learning.